this is Mrs. Often, and I'm happy to be broadcasting today live from my kitchen. Today's topic is solving systems using the elimination method. When do you use this method? Well, I use it with linear systems, particularly those that are not easy to graph, and when it's not easy to solve for a single variable. In truth, even if it is easy to graph and easy to solve for a single variable, the elimination method can be used. So let's begin by solving this system of two equations. As you can see, I could easily solve this by substitution, solving my second equation for x, but instead I'm going to use the elimination method. So I'm going to eliminate that x variable from the second equation, leaving my first equation looking exactly the same. Here's my step 1, 2x minus 3y equals 3. My second equation, I'm going to multiply by -2 and add to the first equation. I'll notate that as R1, first equation, plus -2, R2. So I have -2x plus 2x is 0x. Let's say 2 times -2 is -4, so -3 is -7y. And then 5 times -2 is -10 plus 3 is -7. Okay, so don't really need this 0x. So I get -7y equals -7. Well, this means that y equals 1. Now that I know that y equals 1, I can substitute this value into either one of my original equations. I will substitute it into the top equation, 2x minus 3 times 1 equals 3, and I get 2x minus 3 equals 3. Adding both sides, I get 2x equals 6, or x equals 3. And now I can check 3 plus 2 times 1 is indeed equal to 5. So this is a solution of the system. My solution point is 3, 1. Again, this represents, just as we talked about before, the point where these two lines intersect on the coordinate plane. They intersect at the coordinate point 3, 1. Now, just so you know what these graphical representations look like, two lines could intersect in one point. This one solution is called consistent and independent. We could have two parallel lines, that is, lines that have the same slope but different y-intercepts. These have no solution. They are inconsistent and independent. Finally, my two lines could be exactly the same line. In this case, I have just what appears to be one line here, and that's because the other line lies right on top of it. This has many solutions, in fact, an infinite amount. We call such a system consistent and dependent. Let's look at an example of a system with no solutions. Here we see a system, 2x plus 3y equals 7, and -4x minus 6y. Well, I'm going to do 2r1 plus r2, so multiply this by 2 and add it to the second row. Let's see what happens. If I multiply this by 2, I get 4x plus 6y equals 14. My second equation is 4x minus 6y equals 12. And I do recommend that you write out both equations. I know I didn't in the last one, but it's a good idea. Now here I get 0x. Here my y 0 out as well. 0x plus 0y equals 26. Or 0 equals 26. 0 equals 26 is never true. Since this statement is never true, it means the two lines will never intersect. They are parallel lines, and this system has no solution. We can use this method of elimination for 3 or 4 variable systems as well. In fact, it's called Gaussian elimination, after my celebrity math crush, Gauss. Famous mathematician. Look him up online. Let's see how to solve this with Gaussian elimination. You see I have 3 equations. I have a total of 3 unknowns, even though not every equation has all 3 unknowns in it. My goal is going to be to eliminate the x's in 2 of the equations, eliminate the y's in 1 of the equations, and then I'll have the 3rd equation that just has z in it. So the first thing I'm going to do to get rid of the x's is to do R1, this first equation, minus the 2nd equation. So x minus x is 0x. Y minus negative 2y is 3y. Z minus 4z is negative 3z. And 5 minus 13 is negative 8. You'll notice that right here, I've written the other 2 equations just as they appeared. My middle equation has been replaced. This is called an equivalent system. I don't need to write that 0x, so I'll erase it. And you'll see, hey, look at this. I have 2 equations in y and z. I can solve that. I've done that before. So I'm turning that harder problem into an easier problem. What I'm going to do now is take the 2nd row and subtract the 3rd row from it. I'll keep my 2nd row the same, or my 2nd equation, I should call it, my 2nd equation the same. And 3y minus 3y is 0y. Negative 3z minus 4z is negative 7z. And negative 8 minus 13 is negative 21. Well, if we look at this, I have x, y, z, yz, and just z. This is called row echelon form. It's very useful because now I can use the process called back substitution. I'll solve for z and use that to find the values of the other variables. Okay, so here we are. I've copied over my system in its row echelon form. Now, since negative 7z equals negative 21, z equals 3. And I'll write that down in this ordered triplet. If z equals 3, I can go back to my 2nd equation now. 3y minus 3z equals negative 8. And so this would be 3y minus 9 equals negative 8. So that means that 3y equals 1, and so y equals 1/3. Then, if z equals 3 and y equals 1/3, then x plus y plus z, I have x plus 1/3 plus 3 equals 5. Well, 5 minus 3 is 2. 2 minus 1/3 is 2 and 2/3. Now, I'm not able to draw a nice, elegant picture of what these represent. However, these equations and the equations that we started with that are on the other poster represent planes in space, flat surfaces, in fact, just like these posters. And what this solution represents is the one point where they all intersect. Now, what I want you to do is to think about where in your life you might see 3 planes intersecting, or where you might see 2 planes intersecting. You've probably done this before in your geometry classes, but I'm just asking you to think about it again in preparation for the work that we're going to be doing with systems. So now you've seen an example, you've seen a solution, and you know you can do this Gaussian elimination with 2, 3, 4, or even more. variables. Thanks, and I'll see you next time.